Hi, I want to take a look at a classic example of static equilibrium, trying to balance a ladder against a wall. So in this example, I have a firefighter who's standing on a ladder, but only partway up the ladder, and the ladder is leaning on an otherwise slippery wall that's completely vertical, and it's sitting on a horizontal, flat ground that has some roughness. And the reason why we need that is in order for the ladder to be in static equilibrium, the sum of the forces and the sum of the torques need to be zero, and it needs to be zero in all directions. So if the ladder is leaning on a wall, that means the wall would be pushing that ladder in the opposite direction. So we would need some static friction down at the bottom of the ladder pushing towards the wall to keep the ladder in balance. So the ladder has a weight of 240 newtons, the firefighter has a weight of 960 newtons, and she's standing a distance of 6 meters up an 8-meter long ladder that's leaning on the wall at an angle of 70 degrees. So when we take a look at our free body diagrams that we need to draw, for the ladder, we have an extended free body diagram. And with that extended free body diagram, we're showing our forces and we're showing where those forces are acting on our object. So as always, our weight acts at the center of gravity. So for the ladder, that's the exact center of the ladder. So halfway up the ladder, we have that 240 Newton force pulling downward. Now, the firefighter is the only object that feels the weight of the firefighter. Gravity pulls on her. But she's standing on the ladder. So that means that the ladder is feeling a normal force from the firefighter pushing down. And if I take a look at a normal free body diagram for the firefighter, it shows me that if gravity pulls her down and the ladder's pushing her straight up, the force from the ladder needs to be the same as her weight, so she's going to be pushing on the ladder with a force of 960 newtons straight down. Now the wall is pushing to my left as I've drawn my picture. Looking at the base of the ladder, the wall is pushing to the right, and the ground is pushing up with another normal force acting on that ladder. So when we take a look at the sum of the forces, in the x direction, we have two forces. To the right is the force of static friction. To the left is the force from the wall. Subtract those and I get 0. And that tells me that my force of static friction is equal to the normal force being provided by the wall. Now, ultimately, I want to figure out how much static friction I need to hold everything in place in terms of a coefficient of static friction. Well, we're not quite there yet. We have 1/3 of the information that we need in order to be able to solve. Now, the next piece of information. If I look in the y direction, I have the sum of my forces in the y direction is equal to 0. So I have the normal force from the ground pushing up, I have the weight of the ladder pulling down, and I have the weight of the firefighter translated into a normal force pushing on the ladder, pushing that ladder down. So the normal force from the ground is going to equal the weight of the ladder plus the normal force provided by the firefighter, and 240 newtons plus 960 newtons gives me 1200 newtons of normal force. Now, if you think back to static friction, we said the equation of static friction tells us that the maximum amount of static friction we can get is equal to our coefficient of static friction times our normal force. Well, we found our normal force, so if we want to find the minimum coefficient of static friction that'll work, we need to take the force of static friction that we need and divide by the amount of normal force that we have. So now we're 2/3 of the way there. We have an equation to work with. We know once we find the force from the wall, we found the force of static friction. We still need one more equation though in order to be able to put all of this together. So to do that, we need to take a look at torque. So the sum of the torques has to be 0. And the thing with static equilibrium, since the object isn't rotating, any point you choose is going to give you 0 torque calculated around that point. So my cardinal rule, the more unknown forces you can find, or the more forces, period, that you can find acting at a point where at least one thing is unknown, choose that point for your center for torques. Because any force that's acting at that point has no lever arm, so that means it's generating no torque, period. So for our ladder, we'll choose the base. So that means if we look at our torques, we have the torque from the weight of the ladder that's acting at the center of the ladder. We have the torque from the normal force of the firefighter acting where the firefighter's standing, and we have a torque from the wall pushing away from the wall. So in terms of our rotational directions, we use our right hand, so our force that's going counterclockwise, which is our force that would be acting on our ladder from the wall, that's going to be giving us a positive torque. Now, the force from the weight, the force from the firefighter standing on the ladder, both of those would end up trying to rotate that ladder in the clockwise direction. So we have counterclockwise with 2 clockwise forces, we can get static equilibrium. So what that means then is the torque from the wall minus the torque from the ladder minus the torque from the firefighter equals 0. So that tells us then that the torque that we get from the wall, which is going to be the force from the wall times the length of the ladder, since it's the full distance away from our center of rotation, times the sine of the angle between our force and our ladder. Well, the angle I initially gave of the 70 degrees is from the wall to the ladder. The normal force, though, to the ladder is going to be 90 degrees minus that angle that I gave. So I would have the sine of 90 degrees minus my original angle. And hey, the sine of 90 minus an angle is the same thing as the cosine of that angle. So I could replace that. Now if I take a look at my clockwise torques, the torque from the ladder would be the weight of the ladder times half the length of the ladder, because it acts from the center of mass, which is the center of gravity here, times the sine of the angle between that weight and that ladder. And then the torque from the firefighter, which would be equal to the weight of the firefighter through the normal force the firefighter exerts on the ladder times the distance x that the firefighter is standing up that ladder times the sine of the angle between the downward direction, which is the direction of that normal force, and our ladder, which is that same 70-degree angle. So if I want to simplify things a little bit, I could distribute out the sine of that angle from each term, and then, since I said this is the cosine, I'm going to divide everything by the length of my ladder and the cosine of that angle theta. So where that leaves me is with an expression that says the normal force from my wall is going to equal half my weight, because the length over the length cancels out, plus the normal force provided by the firefighter, which I said is her weight, 960 newtons, times the distance she's standing up the ladder, divided by the total length of the ladder. So here, that would be 6 meters divided by the 8 meter total length of that ladder, and then all of that would be multiplied by the sine over the cosine, which is the tangent of the angle the ladder makes with the wall. So, we're hitting the home stretch. Now, half of 240 newtons gives me 120. 3/4 of 960 gives me 720 newtons. So I'd have 840 newtons total times the tangent of 70 degrees. That gives me 2,310 newtons. So that's the force that the wall is pushing, which means that's the force of friction that we need. So if I take a look at my force of static friction, my force of static friction is also 2,310 newtons. So my minimum coefficient of static friction that I'm going to need I need 2,310 newtons of force with 1,200 newtons of normal force. So 2,310 divided by 1,200 is going to give me a number a little bit less than 2. And you'd think that I would calculate it, but we can do that really quickly. So that's going to give me a coefficient of static friction that's at minimum a little over 1.9. And remember, with static friction, there is no upper limit to it, but 1.9 is still a pretty high number. Now, some of the materials that have super high coefficients of friction, rubbers. If you take a look at a lot of ladders, you notice normally they have rubber feet. That's to give you more friction. The other thing, a 70-degree angle is pretty steep. The steeper you make that ladder, the more friction you need at the bottom, which is why if a friend or a parent ever asked you to help hold a ladder, it's because they needed to work with the ladder at a much more steep angle than it probably should have been. So you're sort of pushing inward to cut the amount of friction that the ladder needed to be providing in order to keep them safe